to start and interrupt me as we go, and we can discuss. That's perfectly fine. So atmospheres, that's my bread and butter. And why? To start, just to tell you a bit some ideas about why we do that. And so, to me, what we're trying to do right now in this decade is really to try to understand every single of those planets as a singular object, like many different planets in solar system. And exoplanets are, a lot of them are very different. So we really need to understand their physical properties, chemical composition as a first step. And then once we manage to get good constraints on those atmospheres and single objects, we can probably put them together and try to link that with what we're discussing with Ravid, interior modems on mixing, evolution, formation, and really try to provide some additional input into planet formation, which, as you all know, has a lot of order one physical phenomena that fight between each other. And so you really need observational constraints. And obviously, in the far future, we all want to find aliens. That's not going to happen right now. But all the techniques I'm going to talk about are basically the same techniques we're going to use on Earth-like planets in the future. So that's where we were in 2022, so pre-James Webb. This is radius of planets as a function of period. The gray points are the detected exoplanets, and the colored points are the ones for which we had some sort of atmospheric characterization. And so you see mainly, our Jupiters were dominating the field, which makes sense, they're easier. We had a few lucky warm Neptunes we could observe, and almost nothing that was below. And obviously, we had nothing still that looks like solar system. We had 19 chemical species in 35 different atmospheres, and that's with like 20 years of HSC data from Charbonneau 2002 to 2022. So now we're 3 years in James Webb, and I changed my plotting routine. So the plot look a bit different, but it's the same. It's radius, a function of period, and that's all the targets in 3 years of James Webb, cycle 1, 2, and 3. So we're down to 150 targets in 3 years, compared to 60 targets in 20 years for HSC. And so we're really having a complete change in our ability to observe those planets and in the range of planets we can observe. So you can see this is reasonably shared between hot Jupiters and Neptunes on rocky worlds. And as you'll see later, each of those data points is 100 times better than what HSC could do. And each of these data points is going to be like, a one-year PhD student work. So there's a lot of manpower needed to, publish all those observations. And I think like roughly like 10% of these are published. We still have a long road ahead. So, you all know solar systems. What we learn from solar system is that sort of diversity, right? You show a picture of a planet to somebody, if he knows a bit about it, he can recognize which planet it is, which tells you they're actually very different. And so our one expectation we have, obviously, is that those 150 planets are going to be harder than stars to put on a 2D diagram to actually look for trends. The advantage we have on solar system planets is that we can spatially resolve things, and that's right. Again, I'm opening open door. I don't know how you say that in English. I'm stating the obvious, but right, we can do cloud tracking on Jupiter, measure directly the wind speed. So we really have spatially resolved data. That's really helpful. On hot Jupiter, though, on exoplanets, usually we don't. That's an example of an output from a model. That's a global circulation model. So it's solved for the temperature, the clouds, the radiative transfer, the atmospheric flows. It's a bit complicated. But this time I took the day side of the model and I plotted the spectra convoluted with your eyes. So this is what it would look like if you were to take your sunglasses and go next to HD 20945. So the red here is the hotspot that shifted and it's glowing in the optical. The blue here is really scattering by the gas with sodium that's actually absorbing a lot of the red part. And this would be like cloud, silicate clouds reflecting on the west part of the planet. And that's kind of what we expect on those planets, at least, which are reasonably representative of the majority of planets we can observe with James Webb right now. And they are, so they are, strong variation, big structures. However, what we observe is this, which is, a 1D spectrum. And we always going to observe this mix of clouds, temperature, and chemical composition. And that's what makes it harder. And that's what makes it complicated in terms of physics, that we need all this physics to just interpret the observation. And to simplify that, I asked Google what this color was, and this is eggplant purple. We know that hot Jupiters are eggplant purple. So what did we have in 2022? This is all the 69 chemical species, the 16 chemical species in the 69 planets that we discovered. They're ranked by temperature here, so the hottest ones are here. And you can see that we've seen a lot of those refractory elements in the very hot planets, because it's so hot that all the refractories are evaporated. And that's a real opportunity compared to solar system planets, that we actually have access to rocks, right, in the atmosphere. We also measure alkalis, and as you go down in temperature, right, those guys condense out, so we don't see them anymore, and we're back at measuring what are volatiles, which I call ice here, and that's more like ground-based high spectral resolution that gets this, and I'll talk about that at the end of the talk, and this is more what we do with Hubble and James Webb. So, how do we do that? We need to separate the star from the planet because they're far away. It's hard. Spatial separation, which I won't talk too much today. Just block the starlight and you see the planet. It's beautiful. So dual stars are usually called, those directly imaged planets, and they form a separate population in itself because they're all young planets, because we do that in the infrared, so we need them to glow in the infrared, and they're really far away. They're like several tens of AU away from the star. We can do spectral separation at high spectral resolution, and that's what we do with ground-based. Again, I'll talk about that at the end of the talk. That's based on the fact that here, the planetary line, as the planet orbit the star, move with time, and that allows us to distinguish them from the stellar lines in the field. And most of what we do with James Webb is temporal separation. So basically transits, and goes in front of the star, and you can measure what's before and what's after. And okay, and so how transit works, I will show this nice animation just because it's nice. But this is from the Imawari satellite, which is a weather satellite. And there were some people in Oxford actually dealing with Earth atmosphere things. So sometimes they look at the moon for, I think it's for calibration purpose. And the good thing about weather satellites is that they do multiple band pass, because all they want to do is spectroscopy. And you can look at 8 micron, where there's no strong absorption bands. And that's what the picture looks like, right? This is the moon saturated. It's going to act as a reference. If you look at inside the ozone band at 9.6 micron, that's what it looks like. So if I switch to look next to the moon, switch back and forth, you see the basic principle of transit spectroscopy. The planet looks bigger in the ozone band. We can also do eclipse, meaning that's when the planet goes behind the star. And so here we usually measure thermal emission, and this can be complicated. This is basically eclipse spectroscopy is much more what we used to deal with on solar system objects, which are thermal emission from the planet. This is an example from Jupiter, which tells you that this is going to be complicated. At 5 micron, where there's, for example, hotspots here, and this is a Juno Cam image of the clouds on Jupiter and the optical, and you can see that the hotspot region here is very dark, that's because there's no clouds, so you can actually see very deep in the infrared. We can do that all along the orbit, and we call that a phase curve. That's where it shows the planet on the star. So you measure the planet on the star flux as a function of time. When you see the day side of the planet, there's more flux, then you get the eclipse here. And then as it goes around, you get towards the night side of the planet, so you see less flux, so transit. By measuring the variation here to there, it's related to the day-night contrast on the planet, so the heat transport. and by measuring the offset here, it's related to the heat, the symmetry of the temperature map on the planet. So is there an offset or is it world symmetry? We'll come back to that at some point. Yeah, so that was Exoplanet's Atmospheres 101, just so everybody could catch up with that. How do we use to do that? We used to do that with those instruments. So that's Hubble, was observing from UV to the near infrared. We had a bunch of optical telescopes, and we had Spitzer that was going for data points, and then just 2 data points when this died. And that's the kind of data we used to deal with. So this is Hubble Space Telescope transits of a planet. Hubble had this very annoying saying that was that Earth was passing in front in the field of view every 90 minutes. It was in low Earth orbit, so if you point a star, then at some point you have to stop observing because the star's behind Earth. And that's why you have gaps everywhere in the observations, which is really annoying when you want to see the transits. Plus, it has systematics. You see the actual observation of the blue points, and so we have to understand the systematics, correct them to get the proper transit fit. Then we were using Spitzer, and when you look at that, you wonder why we were doing that. This is an actual light curve from Spitzer. It's actually a full phase curve of a planet, and you see all those awful systematics, which were related to the pointing, the stellar set that were moving inside the pixel, and the intra-pixel sensitivity was varying. And so we had to do pixel sensitivity maps to correct for that. It was a whole mess. You had to trust a lot of people that this was actually the correct answer when you started with that. And despite that, those very smart data reduction people, they were managing to get something like this. So this is the transit spectrum. So how big is the planet in function of wavelengths? This is the Hubble data, the STIS. This is the HSTWFC3 data. This was the Spitzer data. And that's what our science has been for 20 years. Okay? It was hard. And, 3 years ago now, Christmas, we got our Christmas gift. This guy came in, and that's what we have now. Science. Now we can do science. So the challenge is like, wow, for 2 reasons. First, obviously the error bars here get like 4 times better with HST compared to HST, which is great. But we have this wavelength coverage, right, where we were getting 2 data points. Now we have a beautiful, completely unambiguous CO2 absorption figure. Okay? When we were thinking about Spitzer, you could have like 1,000 different possible species on models that were fit. Well, this is like by eye, it's more than 26 mass detection of CO2. No discussion, CO2 is there. Obviously, and we'll see later, it doesn't mean that it's easier. Because first, now we have to fit that. That's actually not easy. And second, you're going to start having people that are going to start discussing about this very tiny feature here and forget that we have this beautiful 26 detection on the side. So we're always going to try to push the instruments towards new objects, new features, new molecules that we're trying to see. Okay, what do we do when we have a spectra? Well, I personally call the magic unicorn, because it's always my best friend. And the magic unicorn allows you to, the magic unicorn is Louis Wellbank's at ASU. And it allows you to fit the spectra, and you get a beautiful fit. Okay? This is actually a big effort led by Louis and the early release science team, where 300 scientists from atmospheric science, exoplanets, came together to analyze the first batch of 3 James Webb data that we got from NASA. And this is only like 12 models, but there's like more on the paper. And the idea was really to get together as a working group and benchmark the models and try to agree on what was the best solutions. So if you ask everybody to use their own magic unicorn, careful, this is gonna hurt your brain. So this is a movie. This is gonna show the C2 ratio on the metallicity, depending on who you ask in the team to retrieve on the spectra I just showed you. Okay? And that's how it looks like. So it looks a bit better now. Some of them, like this one, they found a bug, and so now this is no more here. But you do see that depending on the single team you ask, you're going to have a spread in the answer on the exact same data set. Okay. And so, fortunately, okay. So first, why do we get that? So what is the magic unicorn? So the magic unicorn is a matrix. Sorry, I didn't tell that to my daughter yet. Magic unicorn is math. So basically, right, you have the Jacobian, which is how the observations at a given wavelength vary with my first physical parameter, with the second physical parameter, etc. This matrix, there are things, we want with the observations we have, and we can debate what we want, obviously. We have like nuisance physics, but we have to deal with it. And there is obviously all the observations we want, but we can't yet have. And, the usual unknowns, the things we don't know we want with the observations we don't know we need. But the real point here is this equation, right? We have the observation, we want the physics, but we have to invert that matrix. And we all know that when you invert matrix, and all the terms get shuffled together. Okay? And what I'm trying to say here is that even if you didn't think about it, maybe physics parameter number n is affecting observation 3. Even if you didn't think about a direct effect, there's going to be degeneracies with another triple degeneracy with another parameter that's going to make it odd. So it's complicated. When you get back to the plot before, okay, sorry, I should have prepared that. Okay, so all this to say that physics is going to be important, right? And there are different approaches in the community. You can be, you can acknowledge your lack of knowledge and be, oh, come on, they're exoplanets. We haven't figured solar system yet. So, I shouldn't make any assumption on how they look like. Let's just parameterize everything and see what the data tells us. And, you can have perfectly parameterized temperature profile, chemistry, clouds, the star, the geometry, etc. Or you can go on the other side of this, which is, oh no, actually I trust my physics. I know radiative transfer actually exists, and I've learned it in undergrad. I know radiative convective equilibrium is actually pretty robust in some cases. I don't know, maybe I know equilibrium cloud model. I think, well, you can't pronounce clouds if it's too hot. Or maybe I'm pretty convinced that my microphysics is spot on. Okay? And so you have this range of possible assumptions. And the funny thing is, obviously, when you put them together with this new data set, so here, the blue is the average of all the movies we were showing before. Okay? You can see that on a given data set, you get pretty wide error bar on your metallicity, like 1-dex. However, if you go to a radiative convective equilibrium model, you get there. Okay, so you get a much more precise solution. Is it a good solution? Well, right? That depends if you trust your best physics. And so that's where I think we're standing now with this new data set, is that we're not going to argue anymore about so much about the data itself. Still going to argue a bit, but not so much about the data itself. But we're going to start arguing about the physics to interpret this data. And that's how we're going to get more and more precise on what we think is happening. And so that's an example of the kind of things we can do. That was a paper led by Lindsay Weiser in ASU. And that's, it's not the main point of the paper, but she's gathered the current measurements in the field, which are done by different teams on different kind of data set on different planets. So that is definitely not an homogeneous sample. And what you can see, the blue ones are all the directly imaged planets. And they seem to lie in this plot as roughly solar metallicity and solar C2O ratio as a broad population, okay? with some scatter. However, if you look at the transiting planets, which are all those guys here, the majority of them seems to be in this corner of high metallicity, low C2O ratio, which I'm not going to try to tell you we know how it deformed because we measure that, because that's more complex than that. But what we can already see is that those two populations from these first 2 years of data seem different. Okay. So we already have some insights, which could be due to different formation mechanism, which could be due to a mass dependence on metallicity, because those are usually more massive because they're easier to observe. So there's plenty of bias to uncover here. But we have the capability now to say that they look different, whereas we didn't have it before. I think that's one step forward. Okay, all good? No questions for now? Go for it. Mm-hmm. No. I mean, all stars are roughly solar plus minus 0.1 days, 0.2.
But not by much.
Yeah, not by much. I don't think that would shift. So, I mean, you don't have stars that are like 20 times solar metallicity.
But the blue ones will all be, for example, below.
Oh yeah. Okay, yeah, this could move a bit down. I agree. Maybe these points orbit a high stellar metallicity, and that would move it down.
And the mass distribution of the planets in the red.
That's the thing. Well, this is a very big planet. Those are like hot Jupiter. Those are like Neptune. So it's a mix. That's a Saturn mass. So this is really a mix. This is just big planet, mostly big planets, and this is a mix. No, this is literature review. So again, we need to do that homogeneously. I think it's going to take a few years to get this kind of homogeneous studies, because first we need to agree on what we think is best. Yeah, so there's, for example, this planet is actually going to move back here in a new paper. There is still, shuffling is going to happen. But some hints of differences is appearing already to me. Yeah.
So the plot is a control for jumping around.
Yeah.
So I don't know from planets, can you give some intuition how it will change the interpretation of the planet based on this value?
Well, it would move that point around here.
Yeah, so that's cool. But I'm asking, like, how does C/O tell us about the planet? What does it tell us about the planet? How much carbon there is?
Yeah, exactly. It's the number of carbon atoms, the number of oxygen atoms. I'll talk about that a bit later. Okay. Yeah.
Yes, but I'm just wondering, so metallicity is some kind of average value for the atoms.
Again, good transition, people, to my next baby, which is one more semi. So I will write in this talk that I'm actually going to talk about 4 or 5 planets, and they happen randomly to be wrong in temperature. So we go from the cold to the hot. So new physics that we're getting. One example is 1107b planet. It's a 770K planet, 30 Earth masses, 1 Jupiter radii, and Rabbit's gonna tell me, oh, it's inflated, and yes, it's inflated. It's a big planet, small mass, 5-day orbit. Okay, so. And that's done with the DTO collaboration and Partin that it's called Manatee, and it's led by Tom Green. So what about this planet? Was 107. So we get, the cool thing with this Manatee group is that they decided to do few planets, but to get a full wavelength coverage for each of them. So we have a lot of data. It makes it actually hard to fit. It took us some time, but we managed to get there. And so what we see in this planet is, so this is all the data set, and those are zoomed in. Again, transit spectrum. This is water, very clear. CO2 here, very clear. This is actually CO, and it's clear because if there was no CO, this would go down much more. So the difference here is CO. And there is a small amount of CH4 here. That's actually filling a bit the gaps between the water and the CO2. And there is a small amount of SO2, which is a fun because it's a photochemical product. Okay? So what is cool here is that we have access to all possible carbon molecules that should be in this atmosphere. CO, CH4, CO2. So there is no more uncertainty about the chemistry and counting the number of carbon atoms. We can just count them. Okay? And that's what's part of our metallicity here. So that'll be carbon plus oxygen over H, basically. Same thing for the oxygen. We also have all the oxygen-bearing species. So before all our before we were measuring only with HST water. So when people were trying to infer carbon to oxygen ratio, they were based on only having observed the oxygen atoms. And so it was very model dependent. Here we can just count the atoms. So the CTO ratio is much more robust than liquid. And the metallicities are much more robust than liquid. So we can measure this metallicity and CTO ratio. And now an interesting question is, with counting the atoms, do the chemical species we see here, the specific mix of CO2, CH4, CO we see, corresponds to what we expect from chemistry in this atmosphere, given the two elemental abundances?
So can I ask, I'm talking about, you say you count the atoms, but actually when I have the signature in the spectrum, I know that this exists. How do you translate it to actually how much there is?
So for the ratio, it's reasonably easy because you have CO2 feature, H2O feature, and the relative height gives you the ratio of CO2 to H2. The absolute abundance, so the metallicity is a bit more complicated, but we have, for example, again, the CO2, which are 3 metal atoms, which then its abundance gonna go as metallicity to the cube, whereas the water goes as simple metallicity. So they don't have the same relationship with metallicity. And so that allows to break some degeneracies that exist on metallicity. Is a ratio of the peaks and the shape of the figures, which is why the high SNR is very important, because with HST, we can't say anything of the shape of that, but with James Webb we can start information of the shape. So, yep.
The oxygen, don't you have any oxygen clouds? I forgot the temperature.
Yes, so we have, we think part of the oxygen is trapped in silicate clouds, for example, MgSiO3, Mg2SiO4. And I agree that's part of, that brings some 30% uncertainty on the oxygen contents. We have to deal with it.
No, yeah.
So some of it is still model dependent, I agree. Okay, still, so you assume you count those atoms. So you're like, okay, I know how many carbon and oxygen atoms there are. What is chemistry telling me? And chemistry is telling you that you should have tons of CH4. So the plain line here is a chemical equilibrium model for CH4 as a function of pressure here. So it's high in the atmosphere. So you would expect a huge amount of CH4. The constraint we measure is the gray posterior here. It's 4 orders of magnitude smaller. That's telling you that if this was chemical equilibrium, the CH4 would be like a huge bump here, which we clearly don't see right now. Yeah. It's clear that this atmosphere cannot be in chemical equilibrium. So one idea to drive this atmosphere out of equilibrium is to this approach of chemical quenching from the deep interior. So we know we have that in Jupiter, or I think it's phosphine in Jupiter, PS3. And CO also is quenched to the deep layers. And the idea is that if you have a temperature profile like the black one here, okay, that gets very hot in the interior, then you get out of the CH4. CH4 likes it cold. That's why we have it on Saturn, on Jupiter, but not on hot Jupiters. And so if you get very hot in the deep layers, then you go towards a place where CH4 is present, strong in chemical equilibrium. And the thing is that because it's so hot here, the chemical time scale are short enough that this deep layer should be in chemical equilibrium. And then if you have vertical mixing, that mixes the parcellous gas from deep layer to the photosphere fast enough, you quench the chemical abundance towards your photosphere. And so the chemical, the repartition of C and O atoms we see at the photosphere is actually representative of what is happening deep in the atmosphere. Okay. And so if we put so we parameterize that with what we call T-ant, which is just a parameterization of the luminosity of the planet, okay, the adiabat where it sits. And so if you do a sigma T-ant for luminosity of 200K, that's way too low, right? You can't deplete CH4 enough. But if we do a hotter model, which is the red model, up to 500K, then that's how we manage to get the CH4. So the really thing we couldn't do before that we can do now, which I think is really interesting, is that we can measure the thermal profile on deep layers that are below the photosphere, meaning that they are not so affected by the stellar light. Because what we had as a problem to link those atmospheres with interior models is that we're looking at the photosphere where we have all the stellar light that dominates the flux. So it's really hard to have any information about the deep flux in the planet. So this is a way to get that. That's really interesting. And this 500K is actually very high for such a planet because it's a low mass planet. So we're saying it's due to tidal heating because it has a slight eccentricity, and that's actually what blows the planet to 1 Jupiter radius, and that gave it the nickname of popcorn planet, which I think was cute because tidal heating puffed the planet atmosphere. Yeah. No. We just say, oh, we need Q that at least this to get this amount. So, please yourself on run models. Okay, let's go to another one. What's ATB? That looks very similar because it's also 1 Jupiter radius. It's also around 800K. It's 171 Earth masses, so it's much more massive than the other ones. It's more like a Saturn mass planet. And so, we can argue is that the same story. This planet, we first published it because that was our first detection of CH4 in an exoplanet, so it was cool. We had it in emission spectrum, so this is a thermal emission from the planet, and transmission spectrum. Right, the CH4 here is the difference in this and that, and here the difference in this and that. Pretty strong signal of CH4 in that. And so we looked at the emission spectrum in more detail. And I'm not going too much into details, but this is comparing some 1D and 3D models. And so trying to fit that spectrum again. Where do I want to go? Okay, and that's what we were getting. And that's an interesting plot. It's showing the metallicity we get as a function of the TNT we get, because there is some degeneracies between PD profile and metallicity. Okay, let me get this clear. So it's the same idea as before, right? We have the CH4, the CO, the CO2, and so the relative abundance are definitely driven by this quenching the deep interiors on the TNT. Okay? The thing is that if you can't use this TNT for some reason, then playing a bit with metallicity will also change the abundance ratio. You can't play too much because we see all the molecules, but you can still play it. And what's fun here is that if you have cloudless planet, you would actually start to have too much flux here in the bandpass where there is not much opacity. So you see very deep in the planet, like the 5-micron hotspot on Jupiter. And and that means you can rule out very high amount of TNT because you would see the photons. Okay? However, if you put clouds in your models, then you're closing those windows, and then you can get the TNT as high as you want, and the constraint from the chemistry gets in and gets you there. Okay? So what I'm trying to tell you is that I'm super excited we get this TNT constraint, but again, physics. Right? Now it's our TNT becomes a parameter we can fit, which we couldn't before. But obviously, the trust on this parameter is going to depend on my cloud physics. One example of the complexity is I asked my student, Michelle Meta, with this picture just after, to run this global circulation model. So there's 3D models solving the primitive equation, the radiative transfer, they predict, this is the usual things they predict, the jet at the equator, the hotspot could be at a substellar point because the tidal log is shifted eastward. Okay? And the night side is colder than the day side, it's latitude, longitude. And if you put clouds in it, that's the kind of cloud distribution you get for an A2S cloud on the WASP ATB. That tells you a bit the complexity because on average, this might look cloudy, but the day side is actually hot enough to evaporate the clouds. Okay? So whether you have clouds or not is actually a complex physics question that we haven't solved yet because it's just starting in the second year, but maybe we'll solve that in 1 year.
Yes.
Yeah.
How much time does it take for the clouds to basically evaporate in the
I encourage you to visit ETH Zurich, Maggie Thompson in the geology department, who does exactly that. She actually put like cloud particles and she blasts them with a laser and see how fast it takes to evaporate them. It's really fast. Like, I mean, when you
So
do
you
that,
can
exactly.
really assume that here I have clouds, no clouds, and they create your
One of the problem is that why do I get no clouds here? It's partly because I had a warming effect of the cloud everywhere that warms enough the atmosphere that destroys the cloud on the daytime. So the feedback is complicated. But once you know the temperature field, it's reasonably safe to assume that if it's hotter than the condensation temperature, your cloud will evaporate reasonably fast.
Once I go back to low temperature, they will condense.
That's a bit more complicated because condensation, if you need homogeneous nucleation, then you can have some kinetic barrier to it. I would say yes, but you know, some microphysics people might say no. Okay, so what else do I have for you? Oh, that's my favorite because that's the one I got observation myself. And now I suffer a lot. So now I'm less happy than 4 years ago when I got the proposal accepted. So this is NGCS 10B. We're up to a real like bona fide hot Jupiter, 1400K, 1 8-day orbit. Oh wait, I have it in this plot within 2. 2 Jupiter mass, 1.2 Jupiter radius. Okay. And so for this one, we choose it, the 0.8 days, because it was the only planet we could fit a full phase curve in a small program in James Webb. Less than 25 hours. 18-hour phase curve fits perfect. And that's what we got. So we got here the eclipse. And you see actually that the eclipse is grazing a bit, which makes everything complicated. Bad luck. Transit, eclipse, day side, night side. Okay. We talked about that before. And hot spot offset due to the shift on the phase curve. It's clearly not symmetrical. So that's how the flux look like as a function of time. So this is actually planet flux over stellar flux. That's why it has this weird shape. But I'll be nice with you and I'll do the planetary science plot just after. So you can see day side, strong flux here. Night side, we stop seeing anything but 3 micron, but we still see the planet at 4 micron. That's really cool. So I take my magic hat, I multiply FP over F star, which is our observational thing, by F star, which is stellar model, and I get FP. And then you're back to a normal planetary science plot where you see the spectrum here from the day side, the data points, that look like a normal SED. You can put on a textbook. So that's the day side, that's the night side, those are the quadrature faces. And so the resolution is pretty low because we're using an instrument called Prism that has the advantage that it does from 0.5 to 5.5 micron in one go. Okay. All the other instrument has to cut this in pieces, and what we wanted for the full phase curve was have the full range in one. And so what you can see here that's really interesting, again, going to talk about chemistry, is so I fit the black bodies here on top, okay, the envelope, like stellar people do to remove the continuum, basically. And I look at the difference with the black body, and I clearly see 2 beautiful absorption features here and there. Okay. And what's interesting is that I see the same absorption features at all phases. Okay, the spectrum is not significantly changing between the blue and the orange. It's the same thing. And that's actually a bit unexpected because the hot part of the planet, the day side, is really well filled by this radiative convective chemical equilibrium model. But the night side in chemical equilibrium, again, should have tons of CH4. Same story as before. Okay? And we don't see it. We don't see it. Yeah, let's not go through that too much. So we don't see this nice CH4. And you're going to tell me, oh, yeah, well, you know, Vivien, you're again telling us the same story. There's a high T-ant that just destroyed the CH4. Well, no. No, because this time we checked that for this planet that's not particularly inflated, okay, I can't increase the T-ant infinitely because that would just make like big planets. Unless I made tons of heavy elements in it, and that causes tons of other problems, right, in terms of formation. And so you can see that's the pressure temperature that the CH4 abundance in equilibrium. Okay? Hot, low pressure, no CH4, high pressure, low temperature, lots of CH4. That's where the day side sits from retrieval on radiative convective models. Okay? That's where the night side sits. Profile from the night side, retrieval on radiative convective model again. And that's our limit on CH4 detection, the blue one. Okay? We know there's less CH4 than this. And we see that although model sits on the left hand of the line, but there's more CH4 than what the data allows. Okay? And if you increase the internal temperature, you're going to increase the deep temperature. And what we want, if we want to remove the CH4 due to vertical quenching, is the deep temperature to cross this dashed line. And you can see that up to this 600K, it doesn't cross on the night side. Okay? So I can't argue, and 600K is already too much for that point. So I can't argue that I have vertical mixing that removes all the CH4 from my photosphere. And so what we think is happening here is yet a different way to deplete the CH4 is the horizontal quenching, meaning that the day side is nicely in chemical equilibrium here, no CH4. And the winds from day to night are fast enough that the chemical composition from the day side actually is transported to the night side, even though that's not, the gas doesn't have time to reach chemical equilibrium. Okay? So those interactions, again, plans are complicated. That's what you should learn from that. We've looked a bit, again, doing those GCM models here. And when you put a GCM model on the data, it doesn't work, which, you know, finally, I'm showing you something that doesn't fit. And I like it because that's where you learn something. This is the day side and night side of the planet. If you do your standard, like, global circulation model with radiative transfer, and it's a common thing. We're expecting this not to work because there's been a trend with Spitzer before where those models are usually too cold on the day side. So what we see, it's below the SCD on the day side, and too hot on the night side. Okay? And so the answer that we've been working on in the past is clouds. If you put clouds on this planet again, so you are talking about oxygen, so these are silicate clouds, MJSIO3. You would expect them again here to evaporate on this side and to form on the night side. Okay? If you put these on the models, that's what the cloud map look like. And the greenhouse effect of the clouds warm the whole atmosphere. So the day side gets hotter, even though there's no cloud there, just by the fact that you have night side cloud. On the night side, even though it gets hotter, the photosphere shifts to lower pressure because I have more opacity. And then I reduce significantly the night side clouds. Okay. Okay, so that was great. Another clue that we have clouds is that we can look at this offset of the phase curve. Remember the phase curve? We can look at the symmetry of the brightness distribution. We used to do that again with Spitzer, which was just here, 1 point here. And now we can do that chromatically with James Webb. So we look at the offset as a function of wavelengths. And what we see is that it's not constant, right? My optical phase curve is not the same, has not the same symmetry as my infrared phase curve. And even in the infrared, I seem to see some things here. What we think is happening, and go there in the infrared for now, is that inside my molecular bond, water and CO here, I'm seeing layers that are at lower pressure in the atmosphere. And as it happens in the GCMs, because you're at lower pressure, it's easier for the radiation to go out. And that means that I cool down faster and I can't transport energy as fast, meaning that my offset is going to be closer to 0, which is more symmetrical. Whereas if I go in deeper layers into the atmospheric windows, I can see deeper in the atmosphere where the energy has harder time to radiate away and transport it more efficiently. So I have a higher hotspot shift due to the circulation. I think that's pretty cool. But again, see, we're using James Webb with this 20 sigma detection of CO2, and I'm arguing with you about those little bumps here, which are really hard to see. Trust me. So again, we're pushing the instruments here. Now, what we're saying is happening here is actually it gets negative because the hotspot is shifted east, meaning that the cloudiest spot, as you saw before, should be shifted west, where it's a bit colder, and that would give you a westward offset here. from the reflected light. So this would be reflected light versus thermal emission. So this to say that we start having, for those hot planets, really a possibility to have a holistic view of the planet. Okay? Really clouds, chemistry, thermal emission, reflected light, 3D, transport, radiative transfer, all this together, we have insight from all those pieces. And that's really important. Really important, why? Because when you do retrieval on a thing like this, and you consider that it's homogeneous, you would get a different answer that if you consider it's not homogeneous.
Vivien, I think you said it's one standard.
Yeah. Yeah.
But why is that the value?
That's what we have. So if you do this cloudless GCM with the wind transport, that's what you get for the offset. So you get too much of an offset, too much transport. If
But
you have
can
the
I just have slower wind?
yes, so you could use what we call drag, which lowers the wind. The problem is that if you lower the wind, you never get those negative offset in the optical and positive offset in the infrared, which was the whole point of this proposal, to show that shift between the two. Plus, if you drag the wind, you will really fast, really easily reduce this offset down to actually zero, down too much, while not strongly yet affecting the day-night contrast. We still need to fit the actual spectrum on the night side. We need a cold night side. If you want to slow the wind to have such a cold night side, then you would have zero offset. But I'm not gonna lie to you. At first, we were super happy because that was the model in the proposal. And that's the data. We're like, wow, right? When does that happen in life? The problem is that the model in the proposal was using radiatively passive clouds, which we know is not true because clouds have a radiative effect. And once you put physics back in, then it breaks everything. It doesn't work anymore. So scratching my head, trying to understand this feedback between cloud and circulation is very frustrating. So we're missing something. So it's good. We have work to do. Cool. All good? Yeah. No, they still get advected. They still have all the cloud thing. By passive, I mean that they're not radiatively active. Meaning they don't affect the radiative transfer. They don't warm the atmosphere. Okay, so I'm done with James Webb. There's 147 other planets we haven't talked about, but you can invite other people. And I want to give you a bit of time on what I think is the other revolution we're having in the exoplanet atmosphere field is the high spectral resolution observations. And that's also recent. So recently we had amazingly good, stable, and high resolution spectrograph put on the biggest telescope on Earth. This was all driven by radial velocity searches. Everybody wants to search for an Earth-like planet and go below the meter per second thing, and so you need resolution, stability, and they work really hard. And then we take them and we use them to actually look at hot Jupiters, which is nice. And that's the amount of atmospheric data we got in the past 5 years, only in the program I know because I'm part of, because the ground-based data is much less public, much less easily available publicly than space-based, so you can't make nice prediction plot easily. So this is only the program I'm involved in, and that's already 50 planets. So you can imagine that if you tie up all the other teams, you're gonna get the same amount of James Webb planet, easy. Okay? So there's really tons of data. And again, there's a hard data set. Each of those data points, 1 year of grad student working. So it's a lot of manpower, and we're a lot behind to get all these data sets. So what's the idea? The idea is that if you zoom in on a spectra, right, you get all those lines. So James Webb looks at the bands, usually, in most of the cases. But here, we're going to try to look at the actual individual lines. So that's the simple idea. The problem is that that's what a error bar looks like. Okay, so I want to observe this with this kind of error bars. It's going to be hard. So the spectrograph gives me the resolution, but not the signal-to-noise ratio. So then we came up with a smart idea. Smart idea is that every single molecule actually has tons of lines. Right? They have like tens of thousands of lines. If you manage to combine all those lines together, you increase your signal-to-noise ratio by square root of the number of lines. So 10,000 of lines is an increase of 100. Easy peasy. So how do we combine them? We use this cross-correlation function, meaning you do a model. That's where physics come in again. And with that model, you cross-correlate the data, and when you have and you shift it in velocity. And if at the expected velocity of the lines, you have a peak in the cross-correlation, like bingo, I found my planet. Okay. It's not at another velocity, but it's here, so it can't be now, it has to be my planet. That's what's typical. And the interesting thing that that's going on is that the planet moves along its orbit. So we expect the line of the planet to move with time. And before last week, I would have shown you a nice simulation on how the planet lines move throughout the orbit. And as it happens, last week, somebody used James Webb. So that's a nice connection on a very good target, very, very bright ultra-hot Jupiters. Look in the CO band. And with James Webb resolution in the CO band, it was enough to actually do this cross-correlation technique. And because James Webb is on the sky, you can look at the full orbit. And that's what David Singh got, which is just amazing. And this is, you're going to see, the radial velocity shift of the cross-correlation function. This is the cross-correlation function. And it shows a maximum in velocity that's going to vary with time. This is what you see in the planetary orbit, the movement of the planet around the star. It's not the RV of the star, it's the RV of the planet itself. Okay? It's beautiful. And because it's in space, we have the full phase curve. And during transit, you can actually see the absorption. And so when we do high res from the ground, we usually only have access to like a small part. Every time we do like a few hours, like 6 hours is already like a big, like ground-based telescope time in one chunk. So we'll talk about, the hottest planet I'm going to talk about is TOI 1518b, 2500K, 2 Jupiter radii, definitely inflated, 2.3 Jupiter mass, not 2.3 Earth mass. It would be really weird. The 2-day orbit. Okay. So really going to this realm of what we call ultra-hot Jupiters. That's Adrien Simonin, grad student in Nice, was working on that, and he found, so I'm not explaining those diagrams, but they're basically a way to combine data along the whole observation. And so he found 14 different chemical species in that planet by this cross-correlation method, including things that are pretty well known in other planets like iron plus, Ca plus, pretty big lines, but also things like VO that interesting we've been searching for a while. Yeah. So the lines are usually a combination, I mean, for the best ones, they're a combination of both. It's the exomorph people and other, the Itron. So what the exomorph people do, for example, they do a lot of complicated quantum calculation. I'm not going to detail here because I wouldn't be able to. That gives them the line strength and line position, but the line position is never very precise, and that's what we need. So then they use experiments to measure precisely the line position, and they combine the two into what they call a marvelized line list, because they like Marvel techniques. So magic, but there is some experiment. All of them are not equal. Some of them are better than others. Like, for example, TIO, for example, we can't really see TIO in high res, and we all think that's because the line list is not sufficiently good. So if you look at the best one, this one, CA plus, more than like 20 sigma detection, you're like, oh, well, 20 sigma, I should see that by eye, right? And indeed, CA plus is actually just a group of a few lines. And that's what the data look like from a telescope. Okay, so you start with that. So you're seeing mainly the star. Here, just all the calcium lines in the star. You have some tellurics here. This is time. So the star and the tellurics don't change with time. Then you have to divide out by the out-of-phase spectrum. So you take the star out and tellurics out. That's what you get. Noise everywhere, not everywhere. On the blue track here, the planetary signal that changes with time during transit. And this one is a stellar residual, which is related to the fact that the planet blocks part of the star. So you can't fully correct for that. Okay, so that's great. So what can we do from this? We can actually, what interests me, so we can measure abundances, and we can talk privately about that and the caveats for that after. But what I'm interested in really is that we can take the planetary track, the expected track here in white, and we can remove it from the data. Because we know the orbital parameters. We can remove the orbital track from the data. When we do that, we get surprises, meaning that if my planet were a perfectly point mass absorbing things along the orbit, I would expect in the planet reference frame to have the track to be perfectly at zero velocity here, because they already corrected for the orbital motion. And we're not saying that. So for the 6 species, what we're saying is systematically that the planet goes from redshift to 0 or redshift to a more blue shifted spectrum. Pretty clear in all of those. A bit differently depending on the species, but the general trend is here. And we've seen that for iron for the 6 other planets already. So there is a clear trend of that. And so to understand that, that was when I was in Oxford, that my grad student used, and especially who's now in Bear, who was in Oxford at the time. So they worked together to put all the Doppler things, the Doppler shift into ELT's code, which was the Monte Carlo radiative transfer code. So you can actually shoot photons and follow them throughout the GCM, and you get the real spectrum. And you can put all the Doppler shift in every single cell of the GCM that you want. It's really an accurate representation of that. And that's what the GCM usually look like. This is day side, night side, this is temperature field. This is the iron plus. This is the iron abundance, so iron plus obviously is more present on the day side because that's where you get ionized. Iron has slightly more distribution. This is the wind speed. We get up to like 8 to 10 kilometers per second, predicted by GCM this planet. And so what we figured out on a previous paper was, why do we get from this red shift to this blue shift? The leading effect is actually a pure geometrical effect. Geometrical effect due to the fact that the planet itself rotates during the transit. So because it's tidally locked, so it has to rotate in transit. At the start of the transit, it means that I'm probing mainly the day side here, where the scale height is high, or the night side here, where the scale height is low. So my signal is going to be dominated by that. Because the planet rotates like this, it's going to be redshifted. At the end of the transit, I get the exact opposite. I'm dominated by this limb, so that's where I probe the day side, and this limb comes towards me, so I'm going to be blue shifted. So during the observation, I expect to go from red to blue, just because the planet has a day-night contrast. I'm probing one limb here and the other limb there. But if I were to do that, you would imagine that the red to blue would be centered, right? So I would imagine this is the data for iron. I would go from red here to blue here, centered on 0. And I'm not. And the difference compared to 0, this is directly linked to the wind speed, the day to night wind speed. So for the first time, we can actually have a direct measurement of wind speed, which I think is going to change a bit our view to analyze these kind of objects, because when you talk to Jupiter people, I've always been amazed by that. They do this fancy GCM models, try to explain the wind speed of Jupiter, the bonding, etc. And like they have no clouds in their models, never. And when you think about it, you're like, well, come on, when I look at Jupiter, right, I see clouds, they have to be important. And they're like, no, but it's fine, because we do cloud tracking, so we have the wind speed. So it's just a purely dynamical problem. We don't need all this complexity, just the dynamics. In exoplanets, up to now, we were always having convoluted data, which means complex model, radiative transfer, etc. But now we're going to get actual wind speed for some of these objects, and we can actually go back to fundamental dynamics, which I'm not doing here because I'm not smart enough, but I think that's a good thing. Okay, so if I take the model from before, it gives me the blue line. So way too much wind compared to what I get. Okay, so I get, the data tells me it's 4 kilometers per second, I get 11 kilometers per second. And data is precisely enough to tell me, well, that's too much, sorry. Yep. Ha, yes. Yes. Not entirely, because, I mean, there are some places where you can make shocks in the planet, but you can think that if you're, yes, there's going to be shock dissipation somewhere. If you imagine, for example, but not everywhere, if you imagine you're like in a jet going around the planet at supersonic velocities and you don't hit a wall, then it's all fine, nothing's going to happen to you. The problem is one, you actually hit something that's lower speed. It actually depends on the circulation. But yes, so dissipation, you're really right. Dissipation should happen. And so there's multiple ideas about dissipation. One of them is shocks, hydrodynamic instabilities. And the one that's fancy these days is ohmic dissipation, because you get ionized atmosphere, you have a magnetic field that's going to drag the atoms, drag the winds. And the way we do that in our models, that we just parameterize it by saying there's a Newtonian, there's a dissipation term, there's a Newtonian relaxation towards zero wind speed with a given time scale. Meaning, I'm going to say, okay, let's assume that if I were to stop the model and just look at inertia, then all the winds will stop after 10 to the 4 seconds. And I'm adding that as a drag force, basically. And what does it do? It does two things. The first thing is that it changes the pattern of the circulation. This is an example with no drag, like the previous model. You get this beautiful jet, hotspot shift, etc. If you add the drag, you start getting into this very day-to-night flow. Completely change the pattern of circulation. And the second thing is that you change radically the wind speed, which is what we actually want to do. And that's an example. No drag, a slightly weak drag. So weak drag, you change the day-night contrast temperature. And very strong drag, you start affecting strong the winds. So we try that on the model. That's what we get. And that's really great. As you increase the drag, you get closer and closer to the data. I'm not going to tell you for sure it's 10 to the 3 or 10 to the 4, but at least I can tell you it has to be a reasonably strong drag. 10 to the 3 seconds, not a long time scale. So it means that it's strong force. The cool thing on this paper is that we can also look at Fe+. So we have 2 different chemical tracers in the atmosphere. They probe different part of the atmosphere. So they probe different part of the winds, the wind pattern. And you can see that, for example, Fe+ is much more affected by the drag here. And so there's, it allows us to distinguish a bit more between the different models. So I'm almost done. It works for all the species, apart from the Ca+, but Ca+ is really high in the atmosphere, so maybe there's something else. We've seen that in a bunch of planets. There's like 6 planets here, and that's from Adrian's presentation, and he has a black background. So I'm sorry, this looks awful. But we see that for a bunch of planets as a message. And so what we're doing now is we're actually trying to measure the wind speed on each of those planets and put that on population plots. That's what Julia Seidel is doing. Currently is a fellow at NIST. And what we get, those are the data points, and they're a bit preliminary. It's not yet an homogeneous sample. So bring me back in 6 months when she's done the actual work. It's literature value for now. What you can see is that at low temperature here, we have small wind speeds. Wind speed is function of temperature. And high temperature gets significantly bigger, up to here like 7 kilometers per second. And then it seems to decrease. What is the weird outlier here?
But the speed is mostly the temperature jet.
No, this is the day-to-night flow that you see, because you're saying the full transit, so you're not dominated by specifically by the equator. So it's really the average flow. That, yeah, exactly. And so what we think might be happening is that between here and there, you increase the temperature, you increase the energy of the system, you increase the wind speed. That's like natural. If there's stronger forcing, Okay, it's stronger forcing, you increase the day-night contrast, you increase the pressure gradient, and so you increase the wind speed. Makes sense. And then, if it's magnetic drag that's dragging the winds, what you would expect is that at some point, you increase the temperature, ionization takes over, because the psi equation has an exponential, basically. And so the drag increases very fast with temperature. You have the wind speed that starts decreasing with temperature. And the fun thing is that this is extremely dependent on magnetic field. So this is a very bit hand-wavy model. It's a model that an energy balance model is basically a heat engine model for Jupiter. So it's not like no MHD because MHD is hard. But it tells you already that orders of magnitude wise, you don't need a large magnetic field to explain this kind of data sets. And there are people doing scaling law of magnetic fields, and they get like hundreds of goes. For hundreds of goes, I would have like zero wind speed for those planets. So that I think with that, we're going to rule out some scaling law parameterization for this. Okay, a few more minutes about the future. You know, this guy's being built. It's amazing. This rotates now. So video, the dome rotates. So it's so exciting. Should be there in like 2030. That's like tomorrow, 25 years. Okay? Why am I excited by that? Well, for all those planets I just told, the ultra Jupiter, we're gonna be able to resolve the lines. So we'll be able to teach the cross correlation spectroscopy, which is great because we won't be model dependent anymore. For now, we need to make a model, cross correlate. It's very convoluted information. Here we'll do like the same as stellar spectroscopy. See the line. It's gonna be like so amazing. And then the other guy I'm excited about, obviously, is this guy, 2040, maybe, if the funding keeps going. It almost hasn't started yet. The funding curve is very slow at the start, and there's big uptake. So government was like, oh, okay, it's for the next guys. We'll see if they actually build it. But the idea here is that this guy's gonna, at the same time, have to discover the Earth-like planets because it's really hard to find those damn Earth-like planets by RV, by transit. All methods are really hard. So they're like, okay, let's find them by direct imaging. But by direct imaging, you need that just to find them. The idea is that this guy would find them and then would characterize them. But by doing that, it will also look at a lot of those giant planets, which I'm excited about. And so we get beautiful light spectra. That's another spectra of Jupiter that HW could get. We'll get this really increase this population much closer to what we have in the solar system, much less exotic planets. So I guess we're all tired, so that's all. Main message, we're really entering the high SNR era, which is wow. But it makes it hard, okay? So now we have to feed high SNR data. Before we had to feed floppy data, that was easy. Now we have to feed high SNR data. What's fun now is that I think we're now going to get limited by the physics. We want to get more precise on those giant planet abundance. We're really going to be arguing about what physics we want in the model and not about what the data is doing. I really think, again, planets are complex and that we need those multi-wavelength, multi-instrument, multi-view single systems. I think I convince you of that with all the 3D, with the vertical mixing, with the winds. It's complicated. So we can finally get statistical sample in 10 years because I don't want to put too much pressure on us, but it should happen at some. Thank you.
Thanks, Vivien, for this great presentation. I think it's already almost 12, but you already have more questions, but we may have time for 2 questions.
Yeah, so very nice talk. One thing I was wondering about is what you put in the last section, which is energy effect, because of course now we have to also invent kind of like new things to this. And I see that the field tends to skip around this point a little bit. So I was wondering what you thought, especially consider expectations, probably one of the things I was.
So for interior, I think people are thinking about it maybe in a better way. I mean, for atmospheres, it's a really complicated problem for MHD people. Why? Because to solve the MHD equation, people from MHD made tons of have made tons of assumptions, which were really good for stars or for Earth's mountain. One assumption is that conductivity depends only on pressure. And we're talking about objects where conductivity comes from very conductive on the day side to 0 on the night side. And that there's no MHD model that can handle that. The second problem is that then there's no zero MHD model that are coupled with radiative transfer for now for this kind of objects. And that makes it that every time they run model with MHD, they're, I mean, again, scaling law, right? Everything is wrong. Like all the parameters they have is wrong. So the wind speed is completely wrong. Then they see how the wind speed varies when they switch on the magnetic field, which is great. And they actually see some oscillations of Tammy Rogers works a lot on that, for example. But I think there is a real technical challenge of coupling those. And personally, I've been back and forth on this because the planets for which this matters, there's not a lot of them. Right? The ultra hot Jupiters, they're very rare outcome planet formations. So there's really not a lot of them. 30, give or take, that we can observe with James Webb. So I was like, okay, those are just too complex. We'll just, no need to put so much effort in it. We'll just skip them, go to the more normal planets. But they're really the best target. They're where we're gonna get the best data. So it's a balance on how much work we need to put onto it compared to the outcome. And I'm so there is two things. So first, obviously for like WASP ATB, where there's this degeneracy between T and of clouds, one of the proposals we put with James Webb is to look at the optical. Because if you have a cloud that's not too deep, you should expect a high albedo. So the first thing is obviously albedo. The second thing that we're starting with, I haven't shown any of these, are MIRI measurements, which is from 5 to 10 micron, where there are cloud resonance features that are specific to the cloud chemical composition. So we had a lot of hope with that. Why? Because we see those in brown dwarf. Brown dwarf have clear silicate features. James Webb saw it in the VHS, like a directly image brown dwarf / planet object, big object. It's very clear. On the transiting exoplanets, so we were expecting the silicate features, but what we seem to be seeing is some like bumpy thing that's a bit shifted compared to where the silicate is. The forsterite and satellite are expected to be. We think we might be seeing quartz clouds instead, but this is still. So the mirror instrument of James Webb is the hardest of all. So we had lots of hope, partly based on models that were a bit over optimistic about the size of the feature we would get, and they happen to be smaller than we were expecting. So it's a bit hard to have fear. But so yes, there is definitely a spectral dependence on the cloud, and that is really one of the hope to help us to know their composition. That plus, as you were saying, clouds should affect the oxygen abundance. So I'm pretty convinced that we should at some point see, if we have good enough data, we should see a small drop in metallicity when the silicate clouds condense out, just because they take the oxygen. That could answer the question.
Okay, well, if there is no further questions, I think we can thank Vivien again.
Ouais, il ne merge pas.
Ouais.
Alors ça,
Est-ce que tu sais à quel moment ça va merger ou si ça va pas?
Alors justement, ça, dans le GCM, ça, c'est les retrievals. C'est le modèle indé. Effectivement, le modèle indé, en fait, c'est pas du tout adapté pour réfléchir au côté de lui.